We're going to go ahead and look at an example of how to use exponential modeling to solve a few questions. In particular, this question involves creating a model by finding a rate of growth or decay. And then the second part will involve us looking at some transformations and some limits. So first, let's go ahead and look at this question here. We have an initial culture size of some bacteria, and the initial size of the population is 8,000. After 1 hour, the bacteria count is 1,000. For part A, this question asks to find a function that models the population after t hours. So our function that we're looking for is n of t equals n0 times e to the rt, where n0 is the initial amount and r is the rate of growth or decay. So I want to make something clear here first. If we're talking about growth here, then r is positive. If we're talking about decay, r is negative. Now here in our problem, we start out with 8,000 specimens. Okay, 8,000 here is our initial count, that's n0. And after 1 hour, it drops to 1,000. So since the population dropped, we're talking about decay. So we need to make sure that our value for r is negative, is less than 0. Now, how can we use this information to figure out what our growth rate is? Well, we can actually start by building the model from what we know. We know after 1 hour, so that's t equals 1, the bacteria count drops to 1,000. So I know that first off, n0 is 8,000. Should write that down as well. And I know that n of 1, the count at 1, is, if I follow this pattern here, n0, which is 8,000, times e to the r times t, and here t is 1 hour. Okay, the question identifies the units of t here, t hours, so t is in hours. Now, we can write this simply, n of 1 is 1,000, that's a count after 1 hour, equals 8,000 times e to the r. Remember that 1 times r is r. Now I need to solve this equation for r to figure out what my growth rate is. So to do that, I'm going to first need to isolate the exponential term here. So I'm going to divide both sides by 8,000. And from that, on the right-hand side, I'll just have e to the r. And on the left, 1,000 divided by 8,000 reduces to 1 over 8, which is a terminating decimal, 0.125. Now, our last step is to figure out how to get r by itself. Well, r is in the exponent. And we remember when we learned about exponential equations that we take logarithms to undo exponentiation in general. So what we're going to do is we're going to now take the natural logarithm of both sides. So we have the natural log of 0.125 equals the natural log of e to the r. And very simply, natural log and e will cancel here, or you can just use the log properties, the fact that natural log of e is 1. So those drop. Now I'm left with r on the right, and on the left, when I evaluate this on my calculator, I get negative 2.079. So r is negative 2.079. But that's not the entire answer. I am asked to find a function. So I use this information to write down my actual function now that I have the value of r. So I will write my function here, n of t equals n0, which is 8,000, we found that earlier, times e to the minus r minus 2.079 times t, and that's my function. With questions like these, it's important to understand what you're looking for so that you get the correct answer that you need. Now let's move on to part B, which says to use the function that we found in part A to find and interpret the population after 1.5 hours. We need to round our answer to the nearest whole number. Now a lot of students will forget what the interpret part means. All this means is write a sentence, meaning after this many hours, there are how many? That's all that part is asking you to do. So first we're going to see what the population is after 1.5 hours. So we're going to take our function here and evaluate it at 1.5. So n of 1.5 is going to be 8,000 times e to the minus 2.079 times 1.5. And when we punch that into our calculator, keeping in mind that we need to make sure that we have everything in the right place, we end up to the nearest whole number, we end up with 354. So that means after 1.5 hours, there are 354 bacteria remaining. It will be 1 point here for finding the actual value and 1 point for writing the sentence to interpret. Now we'll go ahead and do part C and D. These do not require us to actually look back at our original function. Rather, we have a new model here, this model B of t, 500 plus 7500 times e to the minus 0.01 t. This is said to be a better model for what will happen. And in most ecological applications, this will be so perhaps because of a carrying capacity or a lower limit of population. So this is asking us to explain the transformations applied to this function to obtain the picture for b of t. And this requires us to look at 3 parameters here. So each of these numbers here, the 500, the 7500, and the minus 0.01, those tell us transformations that are done. Now, it is only asking us to look at the transformations of e to the minus kt. We don't need to worry about the horizontal stretch or compression. Rather, we need to notice that 7500 indicates a vertical stretch by a factor of 7500. Okay, anytime you have a multiplier in front of the parent function, that means that's a vertical stretch, changing the y values. And then when we add or subtract numbers after, that is a vertical shift. In other words, we move up 500 units. And those are the 2 transformations. Now, from this, we can move on to our last part here, where it says find and interpret the horizontal asymptote of b of t. So for any exponential function, so let's say I have the exponential function f of t equals a times e to the minus kt plus, let's use a lowercase m here, okay? This lowercase m not only is the vertical shift, but it also tells you the horizontal asymptote. When you graph an exponential function, you'll notice that it will decay or grow without bound. In this case, we have a picture here, in this case for b, our picture would look something like this here. We have 500 and our curve would taper off just like this. So we can say that the limit, in this case, the limit as t approaches infinity of a times e to the minus kt plus little m is little m. That means little m is my horizontal asymptote. So if we take the particular case of b of t here, so we go ahead and look back here and look at our b of t. So b of t is 500 plus 7500 times e to the minus 0.01 t. And by the way, this y-intercept is 7500. Okay, if this is b of t. Okay. The horizontal asymptote is the line x equals 500, which means if we want to interpret that, that means if we allow the decay to occur without bound, then the population will decay to 500 specimens. So we can write it as follows, okay? We can write, as time increases, the population will decay to 500. And when it says interpret, that's all you need to do is just write a sentence. What does this mean? In many applications, many functions and their parameters have actual physical meanings, especially when we talk about applications.